Every single time you tap your phone, or boot up your computer, or heck, even start your car, you're kicking off a storm of activity. Billions, and I mean billions of microscopic switches are flipping on and off at insane speeds. So today, we're going to pull back the curtain and look at the fundamental physics that makes that tiny, invisible world actually work.
For more than half a century now, the entire tech world has been marching to the beat of one simple idea, Moore's Law. Now, it's not really a law of physics, it's more of a powerful prediction. It basically says that the number of transistors we can squeeze onto a chip doubles about every 18 months. And this prediction became a self-fulfilling prophecy, driven by pure human ingenuity, and it's the engine behind, well, everything.
But, that relentless pace brings up some really big questions. Like, what is this tiny little device that we keep shrinking over and over again? And how on earth is it possible to pack billions of them into a space smaller than your fingernail? Well, that's exactly what we're going to get into.
So first, let's just take a second to appreciate the scale of this journey. We didn't just wake up one day with billions of transistors. Nope. We started with just a handful, and the story of how we got from there to here, well, it's a story of some truly mind-boggling scaling.
Okay, check out this number, 100,000. This right here is a super important threshold. Once engineers figured out how to cram over 100,000 logic gates, which are just circuits built from these transistors onto a single chip, we officially entered the era of very large-scale integration, or as everyone calls it, Vlsi. This is the bedrock of every modern processor and memory chip in the world today. Right, so at the absolute heart of all this Vlsi magic is the metal oxide semiconductor transistor, or MOS transistor for short. It is the perfect little digital switch. And, as we're about to see, it comes in two essential, and I mean essential, flavors.
So let's meet our two main characters. On the left, you've got the NMOS transistor, and on the right, the PMOS. They might look kind of similar, but they actually operate in completely opposite ways. You can almost think of them as the yin and yang of digital logic. You absolutely need both to create a perfectly balanced system.
So what's the big difference here? Well, it all comes down to what's carrying the current. The NMOS uses negatively charged electrons. It's the speed demon of the two, and it turns on when you give it a digital 1. The PMOS, on the other hand, uses positive charge carriers called holes, and it turns on with a digital 0. It's a little bit slower, but it's way more stable against electrical noise. So the key takeaway is this: one gives us speed, and the other gives us stability.
Okay, we know one turns on with a 1 and the other with a 0, but how? How does that actually happen? Let's zoom way in on the physics of an NMOS transistor to see how it really goes from off to on. So how do we flip this switch? It's basically a three-step process. First, with no voltage applied, the switch is totally off. We call this the accumulation state. Then, as we start to apply a little bit of positive voltage to the gate, it begins pushing away any positive charges underneath it, creating what's called a depletion zone. It's still off though. But then, once we crank that voltage past a certain point, that's when the magic happens. The strong positive field yanks a flood of negative electrons right up to the surface, forming a conductive bridge. That's inversion. The switch is now on, and current can flow like a river.
All right, so we've got our speedy NMOS and our super stable PMOS. They're pretty great on their own, for sure. But when you put them together, oh man, something truly revolutionary happens.
And this is the CMOS revolution. CMOS stands for complementary metal oxide semiconductor. And that word, complementary, is everything. It means we pair a fast NMOS right next to a stable PMOS, creating this perfectly balanced team. It's just like a seesaw. When one is pushed on, the other is automatically pushed off, always in perfect balance.
And this partnership brings these incredible benefits. You get fantastic speed, you get a really efficient use of the chip area, but the absolute killer feature is power. Because one of those transistors is always off, the circuit basically sips power. It barely uses any energy at all when it's not actively switching. This mind-blowing efficiency is what made portable electronics possible. It's why we have laptops and smartphones. And it's why CMOS is still the undisputed king of chip technology today.
But this is where our story takes a hard turn. See, to keep Moore's Law going, we have to keep shrinking these transistors down to almost unimaginable sizes. We're talking just a few dozen atoms across. And when you get that small, the neat and tidy physics we've been talking about, well, it starts to fall apart.
On the left here, you can see the ideal transistor. The gate is the undisputed boss. It says on, it says off, and that's that. But on the right, That's reality. When you shrink the transistor, the source and the drain get so incredibly close that their own electric fields start to interfere. Suddenly, they're fighting the gate for control of the channel. The clean, simple rules just don't apply anymore.
Engineers have a name for this whole collection of new problems: short channel effects. And dealing with them, well, that's the front line in the battle to keep pushing computing technology forward.
So, problem number 1, mobility degradation. Imagine the channel is a superhighway for electrons. In a tiny transistor, the electric field from the gate is so incredibly strong that it basically squishes those electron cars right up against the ceiling of the highway. They can't move freely anymore. They start colliding with the surface and scattering all over the place. It creates a massive traffic jam, and that puts a hard speed limit on how fast the transistor can actually switch.
Then there's problem number 2, threshold instability. Okay, so the voltage you need to turn the switch on is supposed to be a fixed, predictable target, right? Well, now that target is moving. The voltage from the drain can actually reach through the super short channel and start influencing the switch. It lowers the barrier needed to turn on. This effect is called drain-induced barrier lowering, or DIBL, and it basically causes the transistors to turn on when it's not supposed to. And a switch you can't rely on? That's a designer's worst nightmare.
And the final big headache is leakage. In these impossibly tiny devices, off is never truly off. There's always a little bit of current leaking through. But what's even crazier is that the insulator wall that's supposed to block electrons is now only a few atoms thick. And at that scale, quantum mechanics just takes over, and electrons can literally tunnel right through a solid barrier. All this leakage wastes power and creates heat, the two greatest enemies of chip performance.
So you have this beautiful, elegant model of a perfect switch. And then you have the messy, complicated, and frankly weird reality of physics at the atomic scale. For over 50 years, engineers have found unbelievably clever ways to wrestle with these physical limits and come out on top. And the single biggest question that drives this entire multi-trillion-dollar industry is, at its heart, a pretty simple one. How do we keep winning that fight?